The silence of space is not what we imagine. In the vast emptiness between worlds, there exists a symphony of electromagnetic waves, plasma currents, and charged particles dancing to gravitational rhythms that have played since the universe began. And somewhere in that immense cosmic ocean, two small machines built by human hands continue their eternal journey into the unknown, carrying with them not just scientific instruments, but the very essence of what it means to be alive on a small blue world circling an ordinary star. The story begins not with a launch, but with a vision born in the mind of a young graduate student who looked up at the night sky and saw not just distant lights, but destinations. Gary Flandro was working at NASA's Jet Propulsion Laboratory during the summer, calculating trajectories and orbital mechanics with the limited computing power available in the late 1960s. He was searching for efficient routes to the outer planets, those mysterious gas giants that had remained largely unexplored since their discovery centuries earlier. What he found would change the course of space exploration forever. The planets were aligning, not in the mystical sense that astrologers speak of, but in a very real, calculable way that happens only once every 175 years. Jupiter, Saturn, Uranus, and Neptune were arranging themselves in such a configuration that a single spacecraft could visit all four worlds using a technique called gravity assist. Each planet would act like a cosmic slingshot, bending the spacecraft's trajectory and accelerating it toward the next destination. Without this alignment, visiting all four outer planets would require separate missions and decades of time. With it, a single mission could complete what astronomers called the Grand Tour in just 12 years. The opportunity window was narrow. Launch had to occur in the late 1970s, or humanity would have to wait until the middle of the 22nd century for another chance. The pressure was immense. NASA had just experienced the triumph of Apollo, but budgets were tightening and public interest in space exploration was waning. The Vietnam War was draining national resources and attention. Environmental concerns and social issues were taking precedence in the public consciousness. Selling an expensive mission to explore distant worlds that no human would ever visit seemed like a difficult proposition. But there were those who understood that exploration is not merely about the destination, but about the expansion of human consciousness itself. Carl Sagan, already a prominent astronomer and science communicator, became one of the mission's most eloquent advocates. He spoke not just of scientific data, but of perspective, of understanding our place in the cosmos, of the human need to explore and discover. He argued that the Grand Tour represented a once-in-a-lifetime opportunity, that the planets were quite literally aligning to invite us outward, and that to refuse that invitation would be to turn away from our very nature as curious, exploring beings. The mission was approved, though in a scaled-back form. Budget constraints meant that instead of 4 large spacecraft conducting the full Grand Tour, there would be 2 smaller probes initially targeted only at Jupiter and Saturn. The spacecraft would be called Voyager, and they would be twins, each carrying identical instruments and designed with redundancy in case one failed. Their primary mission would focus on the 2 largest planets, but if all went well, if the spacecraft survived the intense radiation environments and the long journey, there was a possibility of extension. Voyager 2, if it could complete its encounters with Jupiter and Saturn successfully, might be redirected toward Uranus and Neptune, completing at least part of Flandro's original vision. The spacecraft themselves were marvels of late 1970s engineering. Each Voyager weighed approximately 722 kilograms and stood taller than a person when fully assembled. The most distinctive feature was the large dish antenna, measuring 3.7 meters in diameter, which would serve as both the spacecraft's primary means of communication with Earth and as a shield against micrometeorites during the journey. Attached to the main body were various scientific instruments: cameras to capture images in both visible and ultraviolet light, spectrometers to analyze the composition of atmospheres and surfaces, magnetometers to measure magnetic fields, and plasma detectors to study the charged particle environment around each planet. Power would come not from solar panels, which would be useless in the dim sunlight of the outer solar system, but from 3 radioisotope thermoelectric generators. These devices, containing plutonium-238, would convert the heat from radioactive decay directly into electricity. At launch, they would produce approximately 470 watts of power, enough to run a few household appliances. But the devices would slowly decay over time, losing approximately 4 watts of power per year, creating an ever-present countdown on the mission's lifespan. The navigation and control systems represented the cutting edge of computer technology for their era, though by modern standards they seem almost comically primitive. Each Voyager carried 3 onboard computers with a combined memory of just 68 kilobytes, less than a single digital photograph today. Yet these simple systems would have to control the spacecraft, manage its instruments, and handle communications across billions of kilometers of space. Every command from Earth, traveling at the speed of light, would take hours to reach the spacecraft, making real-time control impossible. The Voyagers would need to be largely autonomous, capable of making decisions and correcting problems on their own. But perhaps the most famous component of each Voyager was not a scientific instrument at all. Attached to each spacecraft was a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. This edition came at Sagan's insistence. He assembled a team to curate the contents, arguing that while the primary mission was scientific, there was also a symbolic importance to including a message from humanity to anyone or anything that might encounter these artifacts millions of years in the future, long after our civilization had passed into history. The record contained 116 images showing mathematical and physical quantities, human anatomy, landscapes, structures, and daily life from around the world. There were spoken greetings in 55 languages, from ancient Sumerian to modern Mandarin. Natural sounds included surf, wind, thunder, birds, whales, and other animals. Music ranged from Bach and Beethoven to Chuck Berry, and traditional songs from diverse cultures. There was also a message from President Jimmy Carter, which began with words that captured both the ambition and humility of the endeavor. This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. Critics argued that the record was a meaningless gesture, that the odds of anyone finding these spacecraft in the vast emptiness of interstellar space were infinitesimally small, that it was a waste of resources. Sagan countered that the record was not really for potential alien recipients, but for ourselves. It forced us to think about what we would want to say, how we would represent ourselves, what we valued. The very act of creating the record was an exercise in self-reflection, in considering our place in the cosmos and what we hope to communicate about the human experience. Launch day for Voyager 2 arrived on the 20th of August, 1977. Despite being designated as the second spacecraft, it would actually launch first, following a longer trajectory that would allow Voyager 1, launching 2 weeks later, to overtake it and reach Jupiter first. The launch vehicle was a Titan Centaur rocket, one of the most powerful available at the time. As it lifted off from Cape Canaveral, thousands watched, aware that they were witnessing the beginning of a journey unlike any in human history. Voyager 1 followed on the 5th of September, and with both spacecraft successfully in flight, the real mission began. The first months were spent checking out systems, calibrating instruments, and making course corrections. The spacecraft were on trajectories that would take them out of the ecliptic plane, the flat disk in which the planets orbit, eventually heading into interstellar space. But first came Jupiter, looming ever larger in the spacecrafts. Cameras as the months passed. The journey to Jupiter took nearly 2 years. During that time, the Voyager team watched, waited, and planned. They studied all available data from previous missions, particularly the Pioneer probes that had preceded Voyager into the outer solar system. Pioneer 10 and 11 had survived their encounters with Jupiter, proving that spacecraft could transit the intense radiation belt surrounding the giant planet, but they had also revealed just how dangerous that environment was. Jupiter's magnetic field, the largest planetary magnetosphere in the solar system, trapped high-energy particles that could damage or destroy electronic systems. The Voyagers would have to pass through this hellish environment to complete their primary mission. As Voyager 1 approached Jupiter in early 1979, excitement at mission control reached a fever pitch. The spacecraft began returning images that surpassed anything previously obtained. Jupiter appeared not as a static ball with colored bands, but as a dynamic world of swirling storms, complex cloud patterns, and atmospheric features that challenged existing theories. The Great Red Spot, a storm larger than Earth that had been observed for centuries, revealed itself to be an incredibly complex system with internal structure and behavior that scientists had never imagined. But Jupiter was just the opening act. The real revelations came from the moons. Jupiter has 4 large moons discovered by Galileo in 1610, and before Voyager, they were thought to be relatively dead worlds, cold and geologically inert. Voyager 1 shattered that assumption completely. The moon Io, closest to Jupiter, turned out to be the most volcanically active body in the entire solar system. When navigation engineer Linda Morabito was processing images to track the spacecraft's position, she noticed something unusual in a frame showing Io's limb against the darkness of space. There was an umbrella-shaped cloud rising from the surface. It was a volcanic plume, frozen in time by Voyager's camera, erupting hundreds of kilometers into space. The discovery stunned the scientific community. Nothing in the moon's appearance suggested active volcanism. Io should have been frozen solid, its internal heat long since radiated away into space. But theoretical calculations soon provided an explanation. Io orbits so close to Jupiter that tidal forces from the giant planet, combined with gravitational interactions from the other moons, continuously flex and squeeze Io's interior like a ball of clay being kneaded. This tidal heating generates enormous amounts of energy, keeping the moon's interior molten and driving the volcanic activity. Over 8 active volcanoes were identified in the Voyager images, with plumes reaching up to 300 kilometers high. Io's surface was being continuously resurfaced by volcanic activity, making it one of the youngest surfaces in the solar system. Europa presented a completely different mystery. This moon appeared to have the smoothest surface of any solid body in the solar system, covered entirely in water ice, crisscrossed with dark linear features. There were almost no impact craters, suggesting the surface was young and being renewed by some process. The ice appeared to be a shell floating on something beneath. Scientists began to suspect that Europa might harbor a liquid water ocean under its icy crust, kept liquid by the same tidal heating that powered Io's volcanoes, though to a lesser degree. If true, this ocean could contain twice as much water as all of Earth's oceans combined. And where there is liquid water, there's the potential for life. Ganymede and Callisto, the outer 2 Galilean moons, proved to be heavily cratered worlds with ancient surfaces, though they too showed evidence of past geological activity. Ganymede displayed both old, dark terrain and younger, bright terrain, with complex grooved patterns, suggesting episodes of crustal deformation. It was also the largest moon in the solar system, even bigger than the planet Mercury. Voyager 1 also made crucial observations of Jupiter's ring system, discovered by Pioneer just a year earlier. The rings were faint and difficult to image, but Voyager revealed them to be composed primarily of small dust particles rather than the larger chunks of ice found in Saturn's spectacular rings. The particles appeared to come from small moons orbiting within the ring system, constantly replenished by micrometeorite impacts. By April of 1979, Voyager 1 had completed its Jupiter encounter and was speeding toward Saturn. 4 months later, Voyager 2 arrived at Jupiter, following a slightly different trajectory that would set it up for the full Grand Tour. It confirmed and expanded upon its twins' discoveries, imaging the same moons from different angles and under different lighting conditions, revealing new details and features. The complementary observations from both spacecraft provided a 3-dimensional understanding of the Jovian system that would have been impossible from a single vantage point. The journey from Jupiter to Saturn would take nearly 2 years for both spacecraft. During this time, the mission teams had to plan the Saturn encounters with excruciating detail. Every pointing angle, every instrument activation, every image to be captured had to be programmed months in advance and uploaded to the spacecraft's tiny computer memory. There would be no opportunity for real-time adjustments. By the time Mission Control realized something had gone wrong, the spacecraft would already be millions of kilometers past the planet. Saturn has always held a special place in human imagination. Its magnificent ring system, visible even through modest telescopes from Earth, makes it arguably the most beautiful planet in the solar system. But before Voyager, much about Saturn remained unknown. How thick were the rings? What were they made of? How many moons did Saturn have? What caused the different colors and features in the rings? What was the atmosphere like? These questions and hundreds more would hopefully be answered as Voyager 1 approached its rendezvous. In November of 1980, Voyager 1 swept through the Saturnian system. The images that came back exceeded all expectations. The rings were far more complex than anyone had imagined. Instead of a few distinct rings separated by gaps, Voyager revealed thousands of individual ringlets, some braided together in impossible-looking configurations, others showing waves and spiral patterns. The famous Cassini division, long thought to be an empty gap in the rings, actually contained dozens of thin ringlets. There were strange features that looked like spokes radiating across the rings, appearing and disappearing in time-lapse sequences, their origin a mystery that would puzzle scientists for years. The rings themselves were remarkably thin. Despite spanning hundreds of thousands of kilometers in diameter, they were less than a kilometer thick in most places, perhaps only tens of meters in some regions. This made them incredibly fragile and ephemeral on cosmic timescales. The particles making up the rings ranged in size from dust grains to house-sized boulders, all composed primarily of water ice with traces of rocky material. The ice reflected sunlight brilliantly, making Saturn's rings the brightest planetary rings in the solar system. Saturn's largest moon, Titan, was a primary target for Voyager 1. Titan was known to have a thick atmosphere, the only moon in the solar system with a substantial atmosphere, and scientists desperately wanted to know what lay beneath the hazy orange clouds. But here, Voyager encountered one of its few disappointments. The atmosphere was so thick and the haze so opaque that the cameras could not penetrate to the surface. All that was visible was a featureless orange globe. However, the instruments measuring atmospheric composition revealed something remarkable. Titan's atmosphere was primarily nitrogen, just like Earth's, with methane making up a significant fraction. The atmospheric pressure at the surface was 50% greater than Earth's at sea level. The temperature at Titan's surface was measured at 94 Kelvin, cold enough for methane to exist as a liquid. This raised the tantalizing possibility that Titan might have lakes or even oceans of liquid methane and ethane, with weather systems where methane rain fell from the sky and rivers carved channels through frozen water ice bedrock. It was a world with an active hydrological cycle like Earth's, but with methane playing the role that water plays on our world. The implications were profound. Titan became one of the most intriguing targets for future exploration, a place where prebiotic chemistry might be occurring, where the building blocks of life could be assembling in exotic conditions utterly unlike those on Earth. Voyager 1 also discovered new moons, bringing Saturn's total count to more than a dozen. One of these, later named Prometheus, appeared to be a shepherd moon, using its gravity to constrain and shape one of Saturn's rings. Another moon, Mimas, displayed a massive impact crater so large it nearly shattered the moon. The crater made Mimas look remarkably like the Death Star from Star Wars, a resemblance that delighted the public and helped maintain interest in the mission. But Voyager 1's encounter with Saturn came with a cost. The trajectory needed to provide the close flyby of Titan sent the spacecraft on a path that would take it up out of the plane of the solar system, ending any possibility of reaching Uranus and Neptune. Voyager 1 had completed its primary mission spectacularly, but its planetary exploration was finished. It would now head into the outer solar system with no more worlds to visit, becoming an explorer of the space between stars. That left Voyager 2 to complete the grand tour alone. The spacecraft had to be in perfect health and execute its encounters flawlessly, or the opportunity would be lost forever. After its own successful Saturn encounter in August of 1981, which provided complementary views of the rings and moons, Voyager 2 was redirected toward Uranus. This required precise navigation and a perfect engine burn. Any error would cause the spacecraft to miss the planet entirely, and there would be no second chance. The journey to Uranus would take 5 years. During this time, several of Voyager 2's instruments began to show signs of age. The scan platform, which aimed the cameras and other instruments, developed intermittent problems. Engineers on Earth worked to develop workarounds, ways to accomplish the mission objectives, even if the platform failed completely. The spacecraft's power output continued its inexorable decline as the plutonium in the generators decayed. Calculations showed that power would be sufficient for the Uranus encounter, but Neptune, even farther from the Sun and requiring even more time to reach, would push the spacecraft to its absolute limits. Uranus is a strange world. Unlike the other planets, which spin with their axes roughly perpendicular to the plane of the solar system, Uranus is tilted 98 degrees, essentially rolling around the Sun on its side. This bizarre orientation results in extreme seasonal variations. During the Voyager 2 encounter, Uranus's south pole was pointed almost directly at the Sun, meaning the southern hemisphere was experiencing continuous daylight while the northern hemisphere was locked in 42 years of darkness. As Voyager 2 approached in early 1986, uncertainty ran high. Would the featureless blue-green ball resolve into interesting features? Would there be storms, atmospheric dynamics, anything to observe? The first images showed a disappointingly bland world, almost completely featureless, except for a uniform aquamarine color caused by methane in the atmosphere absorbing red light. But as the spacecraft drew closer and instruments measured what cameras could not see, Uranus revealed its secrets. The magnetic field was unlike anything encountered before. Instead of being roughly aligned with the planet's rotation axis like Earth's or Jupiter's, Uranus's magnetic field was tilted 59 degrees from the rotation axis and offset from the planet's center. This created a highly asymmetric magnetosphere that tumbled chaotically as the planet rotated. Charged particles spiraled in complex paths, and the interaction with the solar wind was unlike any other planet. The atmosphere, though appearing calm, had winds blowing up to 900 kilometers per hour. The lack of visible features was due to the extreme cold, about 55 Kelvin at the cloud tops, and the weak internal heat source. Unlike the other giant planets, which radiate more energy than they receive from the Sun, Uranus has very little internal heat. This makes its atmosphere more stable, with less vertical mixing and fewer storms reaching high enough to be visible from space. Uranus's ring system, discovered from Earth in 1977, was confirmed and studied in detail. The rings were dark, composed of material that reflected less than 5% of incident light, making them among the darkest objects in the solar system. They were narrow and sharply defined, constrained by small shepherd moons, just as at Saturn. 11 rings were catalogued, each given numerical designations. The moons of Uranus provided the biggest surprises. Miranda, the innermost of the 5 major moons, appeared to be a geological nightmare. Its surface displayed a patchwork of different terrains, ancient cratered regions next to younger grooved terrain, massive fault scarps reaching 20 kilometers high, and features that looked like frozen-in-place upwellings of ice. One cliff face was 3 times taller than Mount Everest. It looked as if Miranda had been shattered and reassembled multiple times, though the actual explanation probably involved episodes of tidal heating early in its history that partially melted and resurfaced different regions at different times. Ariel showed evidence of past geological activity with valleys and faults cutting across its surface. Umbriel was heavily cratered and dark, with one mysterious bright ring of unknown origin. Titania, the largest Uranian moon, displayed enormous fault systems indicating past tectonic activity. Oberon was heavily cratered with mysterious dark patches on some crater floors. Voyager 2 also discovered 10 new small moons orbiting close to the planet, bringing the total to 15. By the time Voyager 2 left Uranus behind in January of 1986, it had revolutionized our understanding of this distant world. But the mission was not over. Neptune still beckoned, another 3.5 years farther out, orbiting 30 times Earth's distance from the Sun. At that distance, the Sun appears merely as a very bright star, providing 1/900th of the illumination we receive on Earth. Photographing Neptune would be like trying to photograph a dimly lit subject with a very long exposure, complicated by the spacecraft's motion and the need to track the planet precisely. Engineers and scientists spent the years of cruise to Neptune developing new techniques. They would spin the entire spacecraft during imaging to compensate for motion blur, essentially using the whole probe as a tracking mount. The cameras would be pushed beyond their design limits, taking exposures longer than originally planned. The age scan platform, still functioning but increasingly temperamental, would have to perform precisely or the mission would fail. Neptune is the outermost of the giant planets, a world that has never been visited since Voyager 2's single flyby. As the spacecraft approached in the summer of 1989, the planet emerged from the darkness with unexpected vibrancy. Unlike bland Uranus, Neptune displayed dramatic weather systems and dynamic atmospheric features. A great dark spot, reminiscent of Jupiter's Great Red Spot, dominated the southern hemisphere. White, high-altitude methane ice crystal clouds cast shadows on the layers below. The atmosphere showed complex banding and features that changed over hours. Wind speeds on Neptune were measured at over 2,000 kilometers per hour, the fastest in the solar system. This was puzzling because Neptune, like Uranus, receives very little solar energy. Yet while Uranus had a calm atmosphere, Neptune was wildly active. The answer lay in internal heat. Unlike Uranus, Neptune radiates 2.6 times more energy than it receives from the Sun. This internal heat, possibly left over from formation or generated by ongoing differentiation in the interior, drives powerful atmospheric dynamics despite the frigid conditions. Neptune's largest moon, Triton, was the last major target of the Voyager missions and proved to be one of the most fascinating worlds in the entire solar system. Triton orbits Neptune in a retrograde direction, opposite to the planet's rotation, indicating it was captured from the outer solar system rather than forming alongside Neptune. Tidal forces from Neptune have circularized Triton's orbit and will eventually, millions of years in the future, tear the Moon apart when it crosses within Neptune's Roche limit. The surface of Triton proved to be young and active. The temperature, measured at just 38 Kelvin, makes Triton one of the coldest surfaces ever measured in the solar system. Yet despite this extreme cold, Voyager discovered active geysers erupting from Triton's surface, shooting columns of nitrogen gas and dark material up to 8 kilometers high. These plumes drifted downwind in Triton's tenuous nitrogen atmosphere, leaving dark streaks across the pinkish nitrogen ice surface. The surface showed very few impact craters, indicating it had been resurfaced recently in geological terms. There were strange, cantaloupe terrain regions with intersecting grooves and ridges, unlike anything seen elsewhere. Frozen lakes where material had erupted and flowed across the surface before freezing. Ice volcanoes that might have erupted ammonia water mixtures in a process called cryovolcanism. Triton displayed evidence of an incredibly complex geological history, all powered by tidal heating despite the Moon's current circular orbit. Voyager 2 discovered 6 new moons around Neptune and confirmed the existence of ring arcs, partial rings that appeared to be held in place by gravitational resonances with small moons. The complete ring system was mapped, showing several faint rings, some brighter, some barely visible even in Voyager's enhanced images. On the 25th of August, 1989, 12 years after launch and having visited all 4 giant planets, Voyager 2 completed its last planetary encounter. It had traveled nearly 7 billion kilometers, returned tens of thousands of images, made countless measurements, and transformed our understanding of the outer solar system. The grand tour was complete. Both Voyager spacecraft had far exceeded their design lifetimes and primary mission objectives. They had given humanity its first close-up views of half the planets in our solar system, discovered dozens of moons, revolutionized our understanding of planetary atmospheres, magnetospheres, and ring systems. But the story was far from over. Both spacecraft were still functioning, still returning data, still traveling outward at speeds of tens of thousands of kilometers per hour. They were leaving behind the realm of planets and entering the outer solar system, a vast region dominated not by planetary gravity, but by the sun's influence extending billions of kilometers into space. This region, where the solar wind clashes with the interstellar medium, was virtually unexplored. The Voyagers would become the first human-made objects to study this boundary region, the edge of the sun's domain, and potentially cross into interstellar space itself. The mission entered a new phase called the Voyager Interstellar Mission. With the planets behind them, the spacecraft would study the outer heliosphere, measuring the solar wind's properties, cosmic ray intensities, magnetic fields, and plasma waves. They would search for the heliopause, the boundary where the sun's influence ends and true interstellar space begins. No one knew exactly where this boundary lay or what crossing it would feel like. Estimates placed it somewhere between 80 and 120 astronomical units from the sun, distances that would take years or decades to reach. Power became the limiting factor. With the radioisotope generators steadily declining in output, the mission team had to make difficult decisions about which instruments to keep running and which to shut down. One by one, as power dropped, instruments were turned off. The camera system, no longer needed with no more worlds to photograph, was shut down in 1990 to conserve power. Other instruments followed as the years passed, but the core instruments needed to study the interstellar boundary region were kept active, their data still streaming back to Earth across billions of kilometers of space. The spacecraft also had to manage their orientation carefully. They needed to keep their antennas pointed precisely at Earth to maintain communication, but they also needed to orient their instruments to make meaningful measurements. Complex sequences were programmed to balance these needs, rotating the spacecraft periodically while maintaining the ability to send data home. As the Voyagers traveled outward through the 1990s and into the 21st century, they passed beyond the orbits of Neptune and Pluto into the realm of the trans-Neptunian objects. They were in a region of space occupied by countless small ice worlds, remnants from the solar system's formation, including Pluto itself and the newly discovered Kuiper Belt. But the Voyagers were not traveling in the plane of the solar system anymore, having been redirected up and out during their planetary encounters. They would not encounter any of these distant worlds, instead heading into the space between. The data they returned showed gradual changes. The strength of the solar wind varied with the 11-year solar cycle, sometimes stronger, sometimes weaker. Cosmic rays, high-energy particles from outside the solar system, gradually increased in intensity as the Voyagers moved away from the sun's protective influence. The magnetic field showed complex structure, not uniform, but filamentary and turbulent. Then, in 2004, something unexpected happened. Voyager 1 began detecting something strange. The spacecraft had crossed into a new region where the solar wind had slowed dramatically. Instead of the supersonic outflow that had been measured for decades, the wind speed had dropped to zero relative to the spacecraft. This boundary, called the termination shock, marked where the solar wind first encounters resistance from the interstellar medium and begins to pile up. Voyager 1 had reached the edge of the solar wind's dominance and entered a new region called the Helios Heath. Over the following years, both spacecraft crossed the termination shock at different distances, with Voyager 2 crossing in 2007. The difference in crossing distances revealed that the heliosphere was not spherical, but distorted, compressed on one side by the motion of the solar system through the interstellar medium and stretched out on the other side into a long tail. In the Helios sheath, the spacecraft measured increasing cosmic ray intensities and changing magnetic field directions, but they had not yet reached interstellar space. The magnetic field was still the sun's magnetic field, carried outward by the solar wind. True interstellar space would have a different magnetic field orientation, pointing in a different direction entirely, aligned with the galaxy rather than the sun. The crossing was expected soon, but no one knew exactly when it would happen or what the signature would be. The instruments were old, their power supplies declining, time running out. The race was on between the spacecraft reaching the boundary and their inevitable shutdown when power levels became too low to operate the remaining instruments. In May of 2012, Voyager 1 detected a sudden increase in cosmic ray intensity while simultaneously measuring a decrease in lower energy particles from the Sun. The changes suggested a boundary of some kind had been crossed, but the magnetic field had not changed direction. Over the following weeks and months, the particle intensities fluctuated, suggesting the spacecraft was near the boundary, perhaps crossing back and forth as the heliosphere breathed and pulsed with solar activity. Then, on the 25th of August, 2012, exactly 35 years after launch, the particle intensities made a dramatic and permanent change. High-energy cosmic rays jumped to new levels and stayed there. Solar particles dropped to nearly zero. The magnetic field remained steady in a new direction. Voyager 1 had crossed the heliopause. It had entered interstellar space, becoming the first human-made object to leave the solar system and enter the realm of stars. The announcement was not made immediately. Scientists wanted to be absolutely certain, to analyze the data thoroughly, to understand what had happened. Finally, in September of 2013, NASA held a press conference to announce that Voyager 1 had entered interstellar space the previous year. The spacecraft was now 125 astronomical units from Earth, 19 billion kilometers from home, in a region where no spacecraft had ever ventured. Voyager 2 followed 6 years later, crossing into interstellar space in November of 2018 at a slightly different location, providing crucial comparative data about the heliosphere's shape and the nature of the interstellar medium. With both spacecraft in interstellar space, humanity had extended its physical presence beyond the Sun's domain into the galaxy itself. The nature of interstellar space is not what most people imagine. Popular culture often depicts the void between stars as absolute nothingness, a perfect vacuum where nothing exists and nothing happens. The reality is far more complex and infinitely more interesting. The space between stars is filled with an incredibly tenuous medium of gas and dust, magnetic fields that stretch across light years, cosmic rays accelerated to nearly the speed of light, and structures shaped by stellar winds, supernova explosions, and the rotation of the galaxy itself. This is the realm the Voyagers entered, and what they found there challenged assumptions and raised new questions about the boundary between our solar system and the rest of the cosmos. When Voyager 1 crossed the heliopause in 2012, the instruments immediately registered dramatic changes in their environment. The Galactic Cosmic Ray Detector, which had been measuring a steady increase in high-energy particles for years, suddenly jumped to intensities 3 times higher than in the heliosheath. These cosmic rays are atomic nuclei, mostly protons, accelerated to tremendous energies by supernova remnants, pulsars, and other violent processes scattered throughout the galaxy. They travel through interstellar space at speeds approaching light, and the Sun's magnetic field had been partially shielding the inner solar system from their full intensity. Now, with that shield crossed, Voyager was experiencing the true radiation environment of our galactic neighborhood. Simultaneously, the low-energy particle detector registered a precipitous drop in particles originating from the Sun. Throughout the entire mission, this instrument had measured electrons, protons, and heavier ions flowing outward from the Sun as the solar wind. These solar particles had decreased gradually as Voyager moved farther from the Sun, but they had always been present, dominant even in the heliosheath. Now they had essentially disappeared, dropping to less than 1% of their previous levels. The spacecraft had clearly crossed a boundary beyond which the Sun's influence on the particle environment was negligible. But one measurement seemed contradictory. The magnetometer, which had been tracking the direction and strength of the magnetic field throughout the mission, showed no dramatic change when Voyager 1 crossed into interstellar space. Throughout the heliosheath, the field had been oriented in the direction expected, for the Sun's magnetic field carried outward by the solar wind. Scientists had predicted that in interstellar space, the field would rotate to align with the galactic magnetic field, pointing in a completely different direction. Yet the field direction remained essentially unchanged across the boundary. This unexpected result sparked intense debate among the mission scientists. Some argued that perhaps Voyager had not actually entered interstellar space, that the particle changes represented some previously unknown structure in the outer heliosphere, rather than the true boundary. Others suggested that maybe the interstellar magnetic field happened to be aligned similarly to the solar field in this particular direction, a coincidence, but not impossible. A third group proposed that the boundary region was more complex than simple models predicted, that there might be a transition zone where solar and interstellar influences mixed in complicated ways. The answer came from careful analysis of plasma wave data. The plasma wave instrument had been measuring electromagnetic oscillations throughout the mission, detecting waves generated by various processes in the space environment. In the heliosheath, these waves had shown characteristics of the hot, turbulent plasma of the solar wind. But in April of 2013, 8 months after the boundary crossing, the instrument detected a different type of oscillation. These waves had a frequency that depended on the density of the surrounding plasma, and the frequency indicated a plasma density about 40 times higher than in the heliosheath. This was the smoking gun. The plasma in interstellar space is much denser than in the outer heliosphere, even though both are far more tenuous than the best vacuum achievable in laboratories on Earth. The density jump confirmed that Voyager 1 had indeed crossed into a fundamentally different environment. Further analysis showed that the magnetic field puzzle had an elegant explanation. The interstellar magnetic field in the local galactic neighborhood happened to be oriented at a small angle to the Sun's field, small enough that the initial crossing had not produced a dramatic rotation. The field had actually changed direction, but subtly, requiring careful analysis to detect. The plasma wave instrument's detection came from a fortuitous event. A large coronal mass ejection from the Sun, one of the periodic explosions that hurl billions of tons of solar plasma into space, had propagated outward through the heliosphere. When this disturbance reached Voyager 1's location, it created oscillations in the surrounding plasma that revealed its density. Without this natural experiment, confirming the spacecraft's entry into interstellar space would have been much more difficult and taken considerably longer. Voyager 2's crossing into interstellar space 6 years later provided crucial comparative data. The second spacecraft crossed at a different location, roughly 119 astronomical units from the Sun compared to Voyager 1's 122, revealing that the heliopause was closer in the direction Voyager 2 was traveling. This made sense given the heliosphere's asymmetric shape, compressed on the side facing the direction of solar system motion through the galaxy. More importantly, Voyager 2 carried a functioning plasma science instrument that Voyager 1 had lost in 1980, damaged beyond repair by its close flyby of Saturn. This instrument could directly measure the plasma density and temperature, providing unambiguous confirmation of the crossing. When Voyager 2 entered interstellar space on the 5th of November, 2018, the plasma instrument registered a sharp increase in density from 0.19 to 0.13 particles per cubic centimeter. These numbers sound minuscule, and they are about 10 trillion times less dense than Earth's atmosphere at sea level. Yet, in the context of space environments, this represented a significant change, the difference between a region dominated by the Sun and one representing the average galactic environment. The instrument also measured a temperature drop from 35,000 Kelvin in the heliosheath to about 15,000 Kelvin in the local interstellar medium. The comparative data from both spacecraft began to reveal the three-dimensional structure of the heliosphere. The heliopause was not a smooth sphere, but a complex, possibly wrinkled surface that varied in distance depending on direction and probably changed over time with the 11-year solar cycle. The solar wind pressure fluctuated with solar activity, and this would cause the heliopause to breathe in and out, expanding during solar minimum when the wind was weaker and contracting during solar maximum. But the Voyagers were discovering that even beyond the heliopause, the Sun's influence was not entirely absent. Both spacecraft continued to detect solar particles even in interstellar space, particularly during large solar events. Somehow, these energetic particles were leaking across the boundary, perhaps along magnetic field lines that connected the heliosphere to the interstellar medium, or through temporary openings created by instabilities at the boundary. The heliopause was not a perfect barrier, but a dynamic interface where solar and interstellar plasma interacted in complex ways. The magnetic field measurements from both spacecraft revealed another surprise. The field strength in the local interstellar medium was about 3 to 4 nanotesla, significantly stronger than previous estimates based on observations of distant stars and indirect measurements. This has implications for understanding how galactic magnetic fields are structured and how they influence the propagation of cosmic rays through the galaxy. It also affects calculations about the size and shape of the heliosphere, since the interstellar field pressure helps determine where the heliopause forms. One of the most profound findings from the Voyager's interstellar journey relates to the nature of the boundary itself. Scientists had long assumed there would be a bow shock ahead of the heliopause, a region where the interstellar medium flowing past the solar system would create a shock wave, similar to the sonic boom created by a supersonic aircraft. Many models of the heliosphere predicted this bow shock would lie perhaps 10 to 20 astronomical units beyond the heliopause. But as both Voyagers continued their journey beyond the boundary, they detected no such shock. The instruments showed no sudden changes in magnetic field or particle properties that would indicate a shock crossing. This absence suggests that the solar system's motion through the interstellar medium is subsonic, slower than the speed at which disturbances propagate through the local interstellar plasma. Instead of a sharp bow shock, there may be a gentler bow wave or perhaps no distinct boundary at all in that region, just a gradual piling up of interstellar material deflected around the heliosphere. This finding forces a revision of heliospheric models and changes our understanding of how stellar systems interact with their galactic environment. The discovery has implications beyond our own solar system. Other stars also produce stellar winds, and these winds must interact with the interstellar medium in similar ways, creating heliospheres or astrospheres around each star. Understanding our heliosphere's structure and boundary properties helps astronomers interpret observations of other stellar systems. Young, active stars with powerful stellar winds might create bow shocks, while older, quieter stars like the Sun might not. The Voyager data provides the only ground truth, the only direct measurements against which models and theories can be calibrated. As the spacecraft continue their journey deeper into interstellar space, they are measuring properties of the local galactic environment that cannot be measured any other way. The density, temperature, and composition of the interstellar plasma, the strength and direction of magnetic fields, the spectrum and intensity of cosmic rays, all of these parameters are being measured in situ for the first time in human history. These measurements reveal that we live in a relatively warm, low-density region of the galaxy called the local bubble, carved out by supernova explosions over the past 10 to 20 million years. The local bubble is a cavity in the interstellar medium, hundreds of light years across, filled with hot, tenuous plasma left over from the supernovae that created it. Our solar system happens to be located near the edge of this bubble, in a small, denser region called the local interstellar cloud. The Voyagers are measuring the properties of this cloud directly, providing data that astronomers can use to understand how such structures form and evolve. The cloud is moving relative to the solar system at about 23 kilometers per second, and this relative motion shapes the heliosphere's asymmetry. But perhaps the most remarkable aspect of the Voyager's interstellar mission is simply that they are still functioning at all. Both spacecraft are now more than 45 years old, ancient by spacecraft standards, operating billions of kilometers from the nearest repair facility, exposed to the harsh environment of space with no maintenance or replacement parts possible. The fact that they continue to return data is a testament to the quality of their design and construction, to the skill of the engineers who built them, and to the dedication of the mission teams who have kept them operating far beyond their intended lifespan. The radioisotope thermoelectric generators continue their steady decline, losing about 4 watts per year. By 2025, each spacecraft will have only enough power to operate one or two instruments, plus the essential systems needed for communication and attitude control. Mission managers have had to make difficult choices about which instruments to keep running and which to shut down. Each decision represents a trade-off, losing one type of measurement to preserve another, prioritizing science that can only be done by the Voyagers over science that might be done by other means. In 2019, mission controllers began shutting down heaters that had kept various components warm. This was a risky decision because the spacecraft were designed to operate within certain temperature ranges, and allowing components to cool below those ranges could cause failures. But the power saved by shutting off heaters allowed critical instruments to keep running. So far, the gamble has paid off. The spacecraft have proven surprisingly resilient to cold, with components continuing to function at temperatures well below their rated minimums. The spacecraft are also dealing with other age-related issues. Fuel for the thrusters used to maintain spacecraft orientation is running low. Both spacecraft use hydrazine fuel in small thrusters to rotate and maintain their antenna pointing at Earth. After more than 4 decades of operation and countless orientation adjustments, the fuel supply is depleting. Engineers have developed techniques to minimize fuel usage, including using different sets of thrusters that haven't been fired in decades and optimizing the rotation sequences to use the smallest possible amounts of fuel. Communication itself becomes more challenging as the spacecraft recede farther from Earth. The radio signals, traveling at the speed of light, take over 22 hours to reach Voyager 1 and about 18 hours to reach Voyager 2. This means that any command sent to the spacecraft will not be executed until nearly a day later, and confirmation of that execution won't arrive back on Earth until almost 2 days after the command was sent. Real-time control is impossible. Every command sequence must be carefully planned and tested, because by the time controllers realize something has gone wrong, it may be too late to fix it. The signals themselves are incredibly weak. By the time a transmission from Voyager reaches Earth, the radio waves have spread across a sphere billions of kilometers in radius, diluting the signal strength to about 20 billion billionth of a watt. The spacecraft transmit with just 23 watts of power, less than a typical LED light bulb, and this signal must cross the solar system. To receive these whisper-faint transmissions, NASA uses the Deep Space Network, a collection of giant dish antennas located in California, Spain, and Australia, positioned around the Earth so that at least one station always has line of sight to the spacecraft. The largest of these antennas, the 70-meter dishes, can detect signals so weak they would take 9 trillion times the age of the universe to collect enough energy to light a standard light bulb for 1 second. Even with these enormous antennas, the data rate from the Voyagers is just 160 bits per second for Voyager 1 and 160 for Voyager 2, slower than the earliest computer modems. A single image from the Voyager cameras would take hours to transmit at these rates, which is why the cameras have been shut down. The remaining instruments generate less data, mostly numerical measurements that can be compressed efficiently. Despite these limitations, the data continues to flow. Every day, the Voyagers transmit information about their environment back to Earth. Every day, the Deep Space Network dishes point toward the distant spacecraft, collecting the faint signals. Every day, scientists analyze the data, looking for changes, trends, and anomalies that might reveal something new about interstellar space. The mission has become a marathon, a test of endurance for spacecraft, engineers, and scientists alike. The human element of the mission is remarkable in its own right. The team managing the Voyagers today includes people who were not born when the spacecraft launched. They have learned to operate these ancient machines from those who came before, inheriting not just technical knowledge, but institutional memory about the spacecraft's quirks, capabilities, and history. Some team members have worked on Voyager for their entire careers, dedicating their professional lives to keeping these explorers functioning and productive. There is a certain poignancy to the mission now. Everyone involved knows it will end, knows that someday, probably within the next decade, the power will drop too low to operate the transmitter, and the spacecraft will fall silent. They will continue moving through space, of course, carrying their golden records into the galaxy, but they will no longer be able to tell us what they find. The loss will be like losing a dear friend, one who has shared the journey of discovery for half a century. Yet, even as the end approaches, the Voyagers continue to surprise and illuminate. In 2020, Voyager 1 detected an unexpected increase in electron density in the interstellar medium. The plasma wave instrument picked up oscillations indicating the density had increased from about 0.1 to about 0.13 electrons per cubic centimeter. This might not seem like much, but it represents a 30% increase, significant in the context of the already tenuous interstellar environment. The cause remained mysterious. Was it a regional variation in the local interstellar cloud, a compression wave from some distant event, a structure not previously detected? The answer remained unclear, highlighting how much is still unknown about the interstellar medium. Voyager 2, with its functioning plasma instrument, has been measuring directional properties of the interstellar plasma, revealing that the flow of interstellar material past the solar system is not uniform. There are fluctuations and variations, suggesting structure in the local interstellar cloud at scales of tens of astronomical units. This structure might be turbulence, remnants of old supernova shocks, or boundaries between different regions within the cloud. Whatever its nature, it demonstrates that even interstellar space is not homogeneous, but filled with complex dynamic structures. The cosmic ray measurements have also yielded surprises. While the overall intensity of galactic cosmic rays is higher in interstellar space than in the heliosphere, as expected, the detailed spectrum of cosmic ray energies reveals modulation effects that extend surprisingly far from the Sun. Even at distances of 140 astronomical units, Voyager 1 detects variations in cosmic ray intensity that correlate with the 11-year solar cycle. This suggests that the Sun's magnetic influence, while greatly reduced, reaches much farther than the heliopause, affecting cosmic ray propagation across a region larger than previously thought. Scientists have used these measurements to better understand how cosmic rays propagate through the galaxy. Cosmic rays are important for many processes. They ionize interstellar gas, influencing its chemistry and structure. They provide pressure support to molecular clouds where stars form. They may even play a role in Earth's climate and the evolution of life by affecting cloud formation and mutation rates. Understanding their intensity and spectrum helps cosmologists and astrophysicists model these processes more accurately. The magnetic field measurements continue to map the local interstellar field structure. As the spacecraft move through space at about 17 kilometers per second for Voyager 1 and 15 for Voyager 2, they trace out their path through the magnetic field, like a ship trailing a measuring line through the ocean. Over years and decades, this creates a map of the field's direction and strength along their trajectory. So far, the field has remained relatively steady, but scientists expect to eventually encounter boundaries or transitions as the spacecraft move through different regions of the local interstellar cloud, or potentially leave it entirely. One of the intriguing questions is when, or if, the Voyagers might cross into a different interstellar environment. The local interstellar cloud is thought to be a few light-years across, and the Voyagers are traveling at about 3 to 4 astronomical units per year. At this rate, it would take thousands of years to traverse the cloud and enter whatever lies beyond. Yet boundaries within the cloud or the cloud's outer edge might be encountered sooner. If and when such a boundary is crossed, the instruments should detect changes in density, temperature, composition, or magnetic field that would signal the transition. There is also the possibility, however remote, that the Voyagers might encounter unexpected objects. The outer solar system and the space beyond are thought to contain countless small bodies, comets, asteroids, and possibly even rogue planets ejected from other star systems. The Oort cloud, a hypothetical shell of icy bodies surrounding the solar system at distances of thousands of astronomical units, might extend halfway to the nearest stars. The Voyagers are passing through regions where some of these objects might exist, though the odds of actually encountering one are vanishingly small given the vast distances and tiny sizes involved. If such an encounter did occur, the spacecraft probably wouldn't survive. A collision with even a small object at interstellar velocities would be catastrophic. But the probability is so low that it's not a significant concern. Space is unfathomably large, and the Voyagers are very small. They could travel for millions of years without encountering anything larger than a dust grain. Indeed, throughout their entire mission so far, neither spacecraft has detected any impacts significant enough to register on their instruments. The trajectory of each spacecraft is known with high precision. Voyager 1 is heading generally toward the constellation Ophiuchus and will pass within about 1.6 light-years of the star Gliese 445 in about 40,000 years. This star is currently about 17 light-years away but is moving toward us, and the Voyager will pass it as both move through the galaxy. Voyager 2 is heading toward the constellation Pavo and will pass near Sirius, the brightest star in our night sky, in about 300,000 years, though it will still be several light-years away at closest approach. These timescales are almost incomprehensible. 40,000 years ago, humans were still in the Stone Age, living as hunter-gatherers, creating cave paintings in Europe and spreading across the continents. In 40,000 years, human civilization might be unrecognizable, might have spread across the galaxy, might have achieved technological capabilities we cannot imagine. Or we might be gone entirely, victims of catastrophe or our own self-destructive tendencies. But the Voyagers will still be there, silent witnesses drifting through the darkness, the only remaining proof that once, on a small blue world circling an ordinary star, there lived a species curious enough to build machines and send them to the stars. This perspective is both humbling and inspiring. The Voyagers represent the best of human nature: curiosity, ingenuity, perseverance, and hope. They were built during a time of uncertainty and challenge, yet they embodied optimism about the future and confidence in our ability to explore and understand the cosmos. They have succeeded beyond anyone's expectations, transforming from a mission to visit planets into an expedition into interstellar space, from machines with a designed lifetime of 5 years into explorers operating for nearly half a century. The scientific legacy of the Voyager missions is immeasurable. Every planetary science textbook contains Voyager images and data. Every model of the outer planets incorporates Voyager measurements. Our understanding of planetary atmospheres, magnetospheres, rings, and moons was revolutionized by what the Voyagers discovered. The missions revealed worlds of incredible diversity and complexity, each unique, each with its own story. They showed us that the solar system is not a collection of dead rocks and gas balls, but a collection of worlds, each worthy of study, each potentially harboring secrets about the formation and evolution of planetary systems. The interstellar phase of the mission is writing a new chapter in this legacy. For the first time, humanity is directly measuring the space between stars, the galactic environment in which our solar system exists. These measurements provide ground truth for astronomical observations, calibration data for models, and new insights into processes that occur across the entire galaxy. They reveal our neighborhood in the cosmos with unprecedented detail and precision. Yet perhaps the most profound impact of the Voyagers has been cultural rather than scientific. The images they returned, the pale blue dot photograph taken by Voyager 1 showing Earth from 6 billion kilometers away, Carl Sagan's reflections on that image, the golden records carrying human culture into the cosmos, all of these have shaped how we think about our place in the universe. The Voyagers have become symbols of human achievement and aspiration, representing our desire to explore, to understand, to reach beyond our limitations and touch the infinite. The golden records attached to each Voyager spacecraft represent one of the most extraordinary acts of communication ever attempted. They are time capsules, messages in bottles cast into the cosmic ocean, intended for an audience that may never exist, or if it does exist, may not find them for millions or even billions of years. Yet the very act of creating these records forced humanity to confront fundamental questions about who we are, what we value, and what we would want to say if given the chance to speak across the vast gulfs of space and time to unknown minds in unknown places. The idea originated with Carl Sagan, who had been involved with the Pioneer plaques attached to Pioneer 10 and 11, simple gold anodized aluminum plates showing human figures, the solar system's location, and basic scientific information. When the Voyager missions were approved, Sagan saw an opportunity to do something more ambitious. The Voyager spacecraft were larger and could carry more mass. More importantly, they represented humanity's farthest reach into space, and Sagan felt they deserved a more comprehensive message. He convinced NASA to allow the inclusion of a 12-inch gold-plated copper phonograph record encoded with sounds and images that would provide a richer portrait of life on Earth. Sagan assembled a small team to curate the content. The task was simultaneously exciting and overwhelming. How do you represent an entire world, an entire species, all of human culture and achievement in the limited capacity of a phonograph record? What images would you choose? What sounds? What music? Every choice meant excluding countless other possibilities. Every inclusion implied certain values and priorities. The team had just months to complete the project, and they worked with intense dedication, knowing they were creating something that might outlast human civilization itself. The images were selected to show Earth as a place in the cosmos and as a home to life and human culture. They began with scientific diagrams, mathematical and physical definitions to establish common ground with any technological civilization that might find the record, the solar system showing Earth's location, the structure of DNA. Then came images of Earth itself, landscapes and seascapes showing the planet's diverse environments. There were pictures of living things, from microorganisms seen through microscopes to whales swimming in the ocean. Human anatomy and reproduction were included, though these images caused some controversy at NASA, which worried about appearing inappropriate. Images of human civilization showed people from diverse cultures, architecture from different periods and places, technology from Stone Age tools to modern spacecraft. The team tried to show both our accomplishments and our everyday lives, both the monumental and the mundane. There were pictures of children, families, people eating, people working, people making music. The selection was inevitably incomplete and reflected certain biases, but it attempted to portray humanity's diversity and common traits. The sounds were perhaps even more evocative. The record opens with greetings in 55 languages, starting with ancient Sumerian, the oldest written language that had been deciphered, and including languages from around the world. Each greeting is brief, just a few seconds, and they range from formal to casual in tone. The Chinese greeting says, "Hope everyone's well. We are thinking about you all. Please come here to visit when you have time." The French greeting is simply, "Hello, everybody." The English greeting, spoken by Sagan's son Nick, who was 6 years old at the time, says, "Hello from the children of planet Earth." Following the greetings, there's a section of natural sounds from Earth, the rumble of thunder, the crash of ocean waves, the chirping of crickets, the calls of birds, the songs of whales. There are human-made sounds too: footsteps, laughter, a kiss, a heartbeat, the sound of a fire, the chatter of a market, tools being used, a train, a truck, a Morse code signal, the roar of a rocket launch. These sounds were meant to convey the acoustic environment of Earth, the soundscape of a living world. The music selection was the most contentious and difficult part. Of the curation process, music is deeply cultural, emotionally powerful, and incredibly diverse. The team had space for about 90 minutes of music, which meant selecting perhaps 20 to 30 pieces from the entire musical heritage of humanity across all cultures and time periods. It was an impossible task, one that would inevitably leave out far more than it included. They tried to achieve geographic and cultural diversity while also including pieces of exceptional beauty or historical importance. The final selection included Bach's Brandenburg Concerto No. 2 and several other Western classical pieces, recognizing the importance of this tradition while knowing it represented only one cultural approach to music. There was a Javanese gamelan piece, a Japanese shakuhachi piece, a piece played on the Chinese instrument called a kin. There were traditional songs from Peru, Mexico, Zaire, Azerbaijan. There was Louis Armstrong playing jazz, Chuck Berry singing Johnny B. Good, representing American popular music. There was a Navajo night chant, a Pygmy girl's initiation song, a Georgian chorus, an Australian Aboriginal song. Each piece was chosen for its beauty, its cultural significance, or its ability to represent a musical tradition. But the team was acutely aware that any extraterrestrial listeners, if they existed and ever found the record, would have completely different sensory systems, different neurological processing, different cultural contexts. They might not perceive sound the way we do, might not find meaning in rhythm or melody, might be utterly baffled by what we consider beautiful. Or they might hear things in the music that we cannot, patterns and structures invisible to human perception. The record was an act of faith that somewhere, somehow, these sounds might communicate something meaningful. There was also a message from then-President Jimmy Carter, recorded shortly before Voyager 1's launch. It reads, "This Voyager spacecraft was constructed by the United States of America. We are a community of 240 million human beings among the more than 4 billion who inhabit the planet Earth. We human beings are still divided into nation-states, but these states are rapidly becoming a single global civilization. We cast this message into the cosmos. It is likely to survive 1 billion years into our future, when our civilization is profoundly altered and the surface of the Earth may be vastly changed. Of the 200 billion stars in the Milky Way galaxy, some, perhaps many, may have inhabited planets and spacefaring civilizations. If one such civilization intercepts Voyager and can understand these recorded contents, here is our message. This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. We hope someday, having solved the problems we face, to join AEA, Community of Galactic Civilizations. This record represents our hope and our determination and our goodwill in a vast and awesome universe. The record also includes Brainwaves. Anne Druyan, who was the creative director of the project and later became Sagan's wife, had her brain activity recorded for an hour while she meditated on various topics: the history of Earth, human society, the problems facing humanity, her thoughts and feelings about the project itself. This data was encoded onto the record as audio, though it would sound like noise to human ears. The idea was that a sufficiently advanced civilization might be able to decode the electrical patterns and reconstruct something of her thoughts, though whether this is actually possible remains unknown. The most profound aspect of the Golden Record Project was not the content itself, but what it revealed about the creators. In trying to communicate with unknown others, we were really exploring ourselves, examining what we thought was important, what we wanted to preserve, what we hoped to convey. The record is as much a mirror as a message, reflecting back to us our values, our priorities, our self-image. Future humans, looking back at the record's contents, will learn as much about the late 20th century's worldview as any hypothetical aliens might. The cover of the record contains instructions for playing it, including a diagram showing how to determine the proper rotation speed and which direction to play it. There is also a map showing the position of the Sun relative to 14 pulsars, the same map that appeared on the Pioneer plaques, allowing anyone who understands astronomy to determine when and where the spacecraft originated. The record is protected by an aluminum cover, and the entire assembly is designed to last billions of years, far longer than human civilization has existed. Critics of the Golden Record have pointed out numerous issues with the concept. The statistical probability of anyone finding the spacecraft is essentially zero. Space is incomprehensibly vast, and the Voyagers are tiny objects on trajectories that will not pass close to any known stars for tens of thousands of years. Even if a civilization did encounter one of the spacecraft, they would need to recognize it as an artifact rather than a natural object, figure out how to open it, and have or develop the technology to play a phonograph record, a format already obsolete on Earth by the time the Voyagers reached interstellar space. The entire exercise might be seen as a futile gesture, billions of dollars spent to carry a message that will never be received. But defenders of the record, Sagan foremost among them, argued that the statistical improbability of the message being found was not the point. The act of creating the record had value in itself, as an expression of hope, as an exercise in perspective, as a gift to the future. Even if the records are never found by alien civilizations, they might be found by our own descendants millions of years hence, scattered across the galaxy, relics of Earth's first tentative steps into interstellar space. Or they might simply drift forever, silent monuments to a species that once looked up at the stars and wondered, that built machines and sent them outward carrying the essence of what it meant to be human. There is something deeply moving about the golden records now, decades after their creation. The world has changed dramatically since 1977. Many of the languages spoken in the greetings have fewer speakers now, some endangered or nearly extinct. Political boundaries have shifted, nations have risen and fallen. The Cold War that provided the geopolitical context for the space race has ended. Technology has transformed beyond recognition. Some of the people who worked on the record have passed away, including Sagan himself, who died in 1996 at the age of 62. Yet the records continue their journey, carrying voices of the dead through the cosmos, messages from a vanished moment in history preserved for eternity. The records also raise philosophical questions about communication and understanding. When we try to communicate with potential extraterrestrial intelligence, we assume certain commonalities, that they would have senses capable of detecting the record, that they would understand the concept of information storage, that they could decode our symbols and find meaning in our sounds and images. But these assumptions might be entirely wrong. Intelligence could arise in forms utterly unlike our own, with sensory systems that don't include anything we would recognize as sight or hearing, with cognitive processes so different from ours that the very concept of music or visual art would be meaningless to them. Consider the challenge from the opposite direction. If an alien civilization sent us a message encoded in their equivalent of a golden record, would we understand it? Could we recognize it as communication rather than natural phenomena? Would we have the conceptual framework to interpret their symbols, their sounds, their representations? Throughout history, humans have struggled to understand communications from other human cultures, languages that took decades to decipher, artistic and religious symbolism whose meaning was lost when the cultures that created them disappeared. If we have trouble understanding messages from our own species, how could we hope to understand messages from beings who evolved independently on distant worlds? Yet the attempt itself is meaningful. It forces us to think about what communication requires, what understanding means, what it means to be conscious and intelligent. It pushes us to imagine perspectives radically different from our own, to consider existence from viewpoints we can barely conceive. This exercise in radical empathy and perspective-taking is valuable regardless of whether any aliens ever find the records, because it expands our own consciousness and challenges our anthropocentric assumptions about the nature of mind and meaning. The Voyager spacecraft themselves, beyond the golden records, are also messages. Their very existence speaks to certain capabilities and priorities. Any civilization that discovers them will know that they came from a technological society capable of spaceflight, of engineering complex systems, of thinking on interplanetary and interstellar scales. The spacecraft's construction materials, their design, the evidence of their journey encoded in micrometeorite impacts and radiation damage, all tell a story about their origins and their voyage. The trajectory of each spacecraft is itself information. Tracing back the path through spacetime would lead to a small yellow star, indicating the origin point. The radioactive decay in the plutonium power sources, measurable even billions of years from now, would indicate when the spacecraft were launched. The erosion patterns from interstellar dust impacts could reveal something about the environments they pass through. In a sense, the spacecraft are geological records, stratified layers of time and experience accumulated during their journey. But the deepest message might be the simplest. We were here. We existed. We looked up at the stars and dreamed of reaching them. We built these machines with the best of our abilities, and sent them out as representatives of our species, our planet, our moment in cosmic history. We hoped for the future, believed in progress, valued knowledge and exploration. We were curious, creative, and hopeful despite our flaws and limitations. This is the fundamental message the Voyagers carry, transcending the specific content of the Golden Records. It is impossible not to feel a sense of melancholy when contemplating the Voyagers' ultimate fate. They will drift through the galaxy for eons, growing ever colder as their plutonium runs out and they lose the last vestiges of warmth from their power systems. They will be eroded by impacts with interstellar dust, gradually worn away over millions of years. Their trajectories will be perturbed by gravitational interactions with passing stars and giant molecular clouds. Eventually, billions of years from now, they might fall into a star or collide with a planet, meeting a fiery end. Or they might drift forever, frozen artifacts in the cosmic dark. Long before any of that happens, all connection with Earth will have been lost. Within the next decade, the power will decline to the point where the spacecraft can no longer transmit. They will fall silent, unable to tell us what they observe, unable to receive our commands. They will continue moving through space, but alone, cut off from the world that built them. This severance of communication will mark the true end of the mission, transforming the Voyagers from active explorers into passive drift bottles. Yet even in silence, they will continue to be remarkable achievements. They will be the fastest human-made objects ever launched, the farthest travelers, the first spacecraft to enter interstellar space, the first to visit Jupiter, Saturn, Uranus, and Neptune. They will carry the distinction of having worked far beyond their design specifications, having contributed immeasurably to human knowledge, having inspired generations of scientists, engineers, and ordinary people to look up and wonder. Their legacy is secure regardless of what happens in the dark reaches of space they are now exploring. The Golden Records ensure that even if human civilization disappears, even if Earth itself is someday rendered lifeless, evidence of our existence will continue. The records are among the most durable artifacts humanity has ever created, designed to last billions of years. They will outlast our buildings, our art, our writings, perhaps even our planet if the sun expands into a red giant billions of years hence and engulfs Earth. They are our mark on the universe, proof that once, briefly, on one small world, matter organized itself into beings capable of wonder and creation. Some philosophers have argued that the Voyager missions represent the apex of human achievement, the moment when we transcended our planetary origins and became a spacefaring species, however modestly. The missions embodied our highest aspirations, the desire to explore, to understand, to connect across vast distances, to leave something meaningful behind. They showed what we could accomplish when we pooled our resources and intellect toward a common goal, when we looked beyond immediate concerns to embrace a larger vision. Others see the missions as poignant reminders of our limitations. After Voyager, no human spacecraft has visited the outer planets. No mission has replicated the Grand Tour or extended our exploration deeper into interstellar space. The Voyagers represent a high point from which we have arguably retreated, focusing on near-Earth space, on practical applications rather than pure exploration. The golden age of planetary exploration that Voyager exemplified has given way to an era of budget constraints, competing priorities, and diminished ambitions. Both perspectives have merit. The Voyagers are simultaneously triumphs and elegies, monuments to what we achieved and reminders of what we have not done since. They challenge us to recapture that sense of possibility, that willingness to attempt the extraordinary, that faith in the value of knowledge and exploration for their own sake. They ask us whether we are still the species that built them, that dreamed of the stars, that sent golden records into the cosmos as messages of hope. The answer is not yet clear. Human civilization stands at a crossroads, facing challenges that threaten our continued existence. Climate change, nuclear weapons, environmental degradation, political instability. We have not solved the problems that President Carter's message mentioned, the problems that prevented us from joining a community of galactic civilizations. We remain divided, short-sighted, often unable to cooperate even in the face of existential threats. The vision of humanity that the Golden Records presented, a species unified and outward-looking, has not been realized. Yet the Voyagers also remind us of our potential. We built these machines. We sent them across the solar system and beyond. We solved countless technical challenges, created instruments of exquisite precision, managed missions across billions of kilometers. We discovered new worlds, revealed the complexity and beauty of the outer solar system, measured the boundary between our sun's domain and interstellar space. We did this with computers less powerful than modern smartphones, with technology that seems primitive by today's standards, with human ingenuity and determination. If we could do that, what else might we accomplish? The missions also demonstrated the value of international cooperation and the peaceful uses of technology. The Voyagers were built during the Cold War, a time of intense superpower rivalry and the ever-present threat of nuclear annihilation. Yet they represented the opposite of that rivalry: curiosity, exploration, the expansion of human knowledge for the benefit of all. The Golden Records spoke of hope for a unified human civilization, for solving our problems and eventually joining a cosmic community. They were optimistic in a way that was not always justified by the times, but was nonetheless inspiring. As the Voyagers continue their journey, they serve as reminders of what we have accomplished and what we might yet achieve. They are ambassadors not just to hypothetical alien civilizations, but to our own future selves, messages from our past to our future, asking whether we remembered who we were, what we valued, what we dreamed. They are questions posed to the cosmos and to ourselves. Who are we? What do we want? Where are we going? The answers, like the Voyagers themselves, drift somewhere in the vast darkness between stars, waiting to be discovered. The people who built and operate the Voyager spacecraft represent a remarkable continuity of human dedication and expertise spanning nearly 5 decades. From the engineers who designed the spacecraft in the early 1970s to the scientists and technicians who monitor them today, the mission has required thousands of individuals working together across generations, maintaining institutional knowledge, adapting to changing circumstances, and preserving a connection to machines that are now farther from Earth than any human-made objects in history. In the beginning, there were the visionaries: Gary Flandro, who discovered the planetary alignment; Bruce Murray, who fought for the mission's approval; Carl Sagan, who championed its cultural and philosophical importance. These individuals saw possibilities where others saw only problems, recognized opportunities where others saw only costs. They understood that the Grand Tour represented a chance that would not come again in any of their lifetimes, perhaps not in anyone's lifetime for generations to come. They argued, persuaded, and ultimately succeeded in making the mission reality. Then came the builders. Teams of engineers at NASA's Jet Propulsion Laboratory and contractors across the country designed every component, solved every technical challenge, tested every system. They had to create spacecraft that could survive the intense radiation of Jupiter's magnetosphere, withstand the temperature extremes of the outer solar system, operate autonomously billions of kilometers from Earth, and function reliably for years beyond their designed lifetime. Every nut, bolt, wire, and circuit had to be specified, manufactured, tested, and assembled with meticulous care. A single failure could doom the mission. The cameras were particularly challenging. They needed to function across extreme temperature ranges, from the heat of Earth to the cold of Neptune, where temperatures plunge below 50 Kelvin. They needed to capture images in low light conditions billions of kilometers from the sun while the spacecraft was moving at tens of thousands of kilometers per hour. The solution was a camera system that used slow-scan Vidicon tubes, technology that seems archaic now but was state-of-the-art in the 1970s. The spacecraft would compensate for its motion by rotating during exposures, essentially tracking the target to prevent blur. This required split-second timing and precise control, all executed by computers with 68 kilobytes of memory. The spacecraft's computers themselves were marvels of 1970s engineering. Each Voyager carried 3 redundant computers for critical functions, with programming stored in permanent memory that could not be accidentally erased. The computers were built with radiation-hardened components that could withstand the intense particle environment around Jupiter. They had to be reliable beyond anything previously attempted because there would be no second chances, no rescue missions, no way to repair them if they failed. The engineers designed in redundancy wherever possible, backup systems for backup systems, multiple ways to accomplish critical tasks. The power system presented unique challenges. Solar panels would not work in the dim sunlight of the outer solar system, where the sun appears merely as a bright star. The solution was radioisotope thermoelectric generators, devices that convert heat from radioactive decay directly into electricity. Each spacecraft carried 3 RTGs containing plutonium-238, providing 470 watts at launch. The plutonium was manufactured at special facilities and carefully processed to ensure it met the strict specifications. The generators had to be assembled with extreme care, as they would remain hot and radioactive for decades. They also had to be designed to survive a launch failure without releasing their radioactive contents. Testing the spacecraft pushed the limits of available facilities. There were no vacuum chambers large enough to simulate the space environment for the entire spacecraft, so components were tested individually and then integrated with careful analysis of how they would interact in flight. There were thermal tests, vibration tests simulating launch stresses, electromagnetic compatibility tests ensuring instruments wouldn't interfere with each other. Every test revealed problems that needed solving, designs that needed changing, components that needed replacing. The spacecraft that finally launched were the result of countless iterations, thousands of decisions large and small, solutions to problems both anticipated and unexpected. The launch team had their own challenges. The Titan Centaur rocket was powerful, but had experienced failures. Every launch carried risk, the possibility that years of work could end in an explosion or malfunction during the critical minutes of ascent. The launch window was narrow, dictated by the planetary alignment. Miss it, and the opportunity would be gone forever. When Voyager 2 lifted off on August 20, 1977, followed by Voyager 1 on September 5, hundreds of people held their breath, watching telemetry, monitoring systems, waiting to hear confirmation that the spacecraft had reached orbit and separated from the upper stage successfully. The relief when both launches succeeded was immense. Then came the operational phase, and with it, the navigators, the mission controllers, the scientists analyzing data, the engineers troubleshooting problems. These people would spend years, in some cases entire careers, working with the spacecraft. They learned to think like the machines, to understand their capabilities and limitations, to coax maximum performance from aging systems. They developed intimate knowledge of every quirk and idiosyncrasy. They knew which instruments were most reliable, which systems needed careful monitoring, which thrusters to use for different maneuvers. Linda Morabito's discovery of volcanic activity on Io exemplifies the human element of the mission. She was processing images to determine the spacecraft's exact position, routine navigation work, when she noticed something that wasn't supposed to be there, a plume rising from the moon's surface. Someone less observant might have missed it. Someone less curious might have dismissed it as an artifact or error. But Morabito recognized it as potentially significant, reported it to the science team, and helped spark one of the mission's greatest discoveries. Individual attention, expertise, and dedication made the difference between a piece of data being ignored and a revolutionary finding being recognized. The imaging team faced unique challenges throughout the mission. Every image had to be planned months in advance, programmed into the spacecraft's limited memory, executed perfectly during the brief flyby windows. There was no opportunity for do-overs. If something went wrong, if an image was poorly exposed or aimed at the wrong target or lost in transmission, that opportunity was gone forever. The team spent countless hours planning each sequence, calculating exactly where each planet and moon would be at each moment, determining optimal camera settings, prioritizing targets when time and memory constraints meant choices had to be made. Candy Hansen, who worked on the imaging team, later recalled the intensity of the encounter periods. When the spacecraft was making its close approach to a planet, Images would stream back to Earth for hours or days. The team would be in constant operation, monitoring the data, looking for problems, making last-minute adjustments to upcoming sequences when possible. Sleep became a luxury. The images themselves were breathtaking, revealing worlds no human had ever seen up close, but there was little time to simply admire them. Each image needed analysis, comparison with predictions, assessment of what it revealed about the target. The engineers faced their own crises. When Voyager 2's primary radio receiver failed shortly after launch, the spacecraft automatically switched to its backup receiver. This was exactly what the redundant design was supposed to do, but the backup receiver had a problem. Its tracking loop capacitor was faulty, causing the receiver to drift out of sync with transmissions from Earth. The engineers had to develop a new way to communicate with the spacecraft, adjusting their transmission frequency to compensate for the drift. A workaround that required constant monitoring and adjustment, but allowed the mission to continue. During Voyager 2's encounter with Saturn, the scan platform that aimed the cameras and other instruments became stuck. It would not rotate properly, threatening the entire encounter sequence. The engineers had to diagnose the problem from billions of kilometers away with limited telemetry. They developed careful procedures to exercise the platform gently, working it free without causing further damage. They succeeded, though the platform remained problematic for the rest of the mission, requiring careful management and gentle handling. This kind of improvisation and problem-solving became routine, a constant battle to keep the aging spacecraft functioning. Suzanne Dodd, who has been the Voyager project manager since 2010, oversees a team that has shrunk considerably from the mission's peak, but remains dedicated to keeping the spacecraft operational as long as possible. She describes the challenge of managing systems designed and built before most of her team members were born, operating far beyond their intended lifetime, with less power available every year. The team must constantly prioritize, deciding which instruments to keep running and which to shut down, which systems are essential and which are expendable. Every decision is difficult because every instrument is still capable of returning valuable data, but the power budget is inexorable. The team has developed creative solutions to extend the mission. In 2017, they fired Voyager 1's trajectory correction thrusters for the first time in 37 years. These thrusters had been dormant since the Neptune encounter, but were needed because the primary attitude control thrusters were degrading and using fuel inefficiently. The engineers had to figure out whether thrusters that had been idle for decades would still work, whether the fuel lines would be clogged, whether the ancient plumbing could handle the pressure. They ran tests, analyzed data, and finally sent the command to fire the thrusters. The wait for confirmation was tense, but the thrusters worked perfectly, buying additional years of mission life. Similar engineering creativity has been applied to thermal management. As instruments have been shut down to save power, the team has also turned off heaters that kept components warm. This risks damaging systems that were not designed to operate at such low temperatures, but it saves precious power. So far, the spacecraft have proven remarkably resilient to cold. Components continue functioning well below their rated temperature minimums, a testament to the quality of their construction and the engineers' conservative design margins. The Deep Space Network operators represent another critical human element. These are the people who actually communicate with the spacecraft, pointing enormous dish antennas at precise coordinates in the sky, tracking the spacecraft as Earth rotates, receiving the faint signals, and transmitting commands. The DSN operates 3 complexes positioned around the globe in California, Spain, and Australia so that at least one station is always in view of deep space missions. The operators must coordinate with multiple missions, scheduling time on the antennas, prioritizing urgent communications, managing the network's resources. For the Voyagers, they must point with extraordinary precision at targets so distant that even light takes nearly a day to make the round trip. The scientists analyzing Voyager data span multiple generations now. Some began their careers during the initial planetary encounters, young graduate students or postdocs processing those first images from Jupiter's moons or Saturn's rings. They built their careers on Voyager data, wrote their dissertations on Voyager discoveries, became professors and mentors to new generations. Their students are now analyzing the interstellar data, studying the heliopause crossing, measuring properties of the local interstellar medium. There's a direct lineage from those early scientists to today's researchers, a passing of knowledge and expertise across decades. Ed Stone has been the project scientist since before launch, one of the few people to maintain continuous involvement throughout the entire mission. In interviews, he speaks about the privilege of working on Voyager, of being part of humanity's first journey into interstellar space. He describes the mission not as a series of planned encounters and discoveries, but as a journey of continuous revelation, where the spacecraft kept finding things no one had predicted, where nature proved more complex and interesting than any model or theory. His longevity with the mission provides continuity and institutional memory that has been invaluable. But there is also poignancy in the aging of the mission team. Many of those who built the spacecraft, who guided them through the planetary encounters, who made the crucial decisions and solved the critical problems, have retired or passed away. With them goes irreplaceable knowledge and experience. The current team has worked hard to document everything, to preserve the expertise, to ensure that the spacecraft can continue to be operated effectively even as personnel change. But there are always subtleties, intuitions, and historical context that resist documentation, knowledge that exists only in the minds of those who lived through the experiences. The mission has also had to adapt to changing institutional structures and priorities at NASA. Budgets have fluctuated over the decades, sometimes generous, often tight. The Voyager team has had to justify continued funding year after year, competing with other missions and priorities. They have had to demonstrate that the science returned remains valuable, that the spacecraft are still functional and worth supporting, that the mission continues to serve NASA's objectives. This is not always easy when the spacecraft are exploring regions of space that lack the visual appeal of planetary encounters, when the data consists of particle counts and field strengths rather than stunning images. Public interest has also waxed and waned. During the planetary encounters, Voyager was front-page news. Images from Jupiter, Saturn, Uranus, and Neptune captivated public attention, appeared in newspapers and on television, inspired a generation of scientists and engineers. But during the long cruise phases between encounters, media coverage dropped. The interstellar mission, while scientifically fascinating, lacks the visual drama of planetary flybys. The team has worked to maintain public engagement, to communicate the significance of the interstellar findings, to remind people that these spacecraft are still out there, still exploring, still sending back data from farther away than anything else humans have ever built. Social media has helped in recent years. The mission maintains active accounts on various platforms, sharing updates, explaining discoveries, commemorating milestones. Anniversaries of the planetary encounters generate renewed interest. The announcement of Voyager 1 entering interstellar space in 2013 received widespread coverage, reminding people of the mission's existence and importance. The team has learned to use these moments to highlight the ongoing mission, to seek public support that can help secure continued funding. There are also efforts to preserve the mission's legacy for future generations. The raw data from the spacecraft, both from the planetary encounters and the interstellar mission, is archived in NASA's planetary data system and other repositories. The images have been reprocessed with modern techniques, enhancing details that were difficult to see in the original processing. New generations of scientists can analyze this data, making discoveries that the original teams might have missed, asking questions that weren't thought of at the time. The data will outlast the mission itself, continuing to yield insights for decades or even centuries. The golden records have taken on a cultural life of their own. The contents have been released publicly, allowing anyone to see the images and hear the sounds that are speeding through space on the Voyagers. There have been books, documentaries, and even a vinyl release of the record's audio contents. Artists and musicians have created works inspired by the golden records. They have become iconic symbols of human aspiration and cosmic loneliness, representing both our desire to connect and our isolation in the vast universe. Carl Sagan's widow, Anne Druyan, has become a guardian of the Voyager's cultural legacy. She speaks and writes about the mission's meaning, about the vision that motivated the Golden Records, about what the Voyagers represent for human civilization. She reminds audiences that the spacecraft carry a message of hope from a species that, despite its flaws and problems, looked to the stars and tried to say something meaningful. She argues that the Voyagers' greatest value might be not in the science they return, but in the perspective they provide, the reminder of our place in the cosmos. The engineers and scientists working on Voyager today know that their time with the spacecraft is limited. Within the next few years, power levels will drop below the minimum needed to operate the transmitter and maintain communications with Earth. At that point, the spacecraft will fall silent. They will continue moving through space, their instruments still functioning for a time, still measuring the environment around them, but unable to share what they find. Eventually, the power will drop below even the minimum needed for the instruments, and they will go dark entirely, cold and dead, drifting through interstellar space with only the Golden Records remaining as evidence of their purpose. The team is working to extract maximum value from the remaining time. They are carefully managing the power budget, making strategic decisions about which instruments to keep operating and for how long. They are analyzing data in real time, looking for significant findings that might change priorities. They are preparing for the inevitable moment when they receive the last signal, when the spacecraft that have been constant companions for decades finally go silent. That moment will be profoundly emotional for everyone involved, the end of a relationship that has lasted nearly half a century. There are discussions about what should happen to the deep space network time currently allocated to the Voyagers after communications end. That time represents a valuable resource that could be used for other missions, but there are also suggestions that the network should continue listening for the Voyagers, just in case. Perhaps an unexpected power management success or a fortunate equipment behavior might allow one more transmission. Perhaps there will be a final message, a last gasp from the far darkness. Most engineers think this is unlikely, that when the end comes, it will be final and absolute. But there is something appealing about the idea of keeping the channel open, of continuing to listen for voices that almost certainly will never speak again. Some team members have expressed a desire to be present when that last signal arrives, to bear witness to the moment when humanity's first interstellar explorers fall silent. They have spent years or decades working with these spacecraft, solved countless problems, celebrated numerous discoveries, felt pride and frustration and wonder in equal measure. The spacecraft are not just machines to them, but something more. Entities with personalities shaped by their unique histories and quirks. The end of communication will be a loss, a severing of connection that will mark the conclusion of the active mission phase and the beginning of the Voyager's long, silent journey into the unknown. Yet even after silence falls, the mission's legacy will continue. The discoveries made by the Voyagers have fundamentally changed our understanding of the solar system and the space beyond. Every planetary science textbook will contain Voyager data for generations. The images of the planets and moons will continue to inspire wonder. The measurements of the interstellar medium will provide baseline data for future missions. The spacecraft themselves will continue to drift through space, monuments to human curiosity and ingenuity, carrying their golden records toward unimaginable futures. And the people who worked on the mission will carry their own memories and lessons. They will tell stories of the challenges they faced and overcame, the discoveries they made, the problems they solved. They will pass on their knowledge to the next generation of spacecraft designers and mission operators, sharing what they learned about reliability, redundancy, and the importance of building systems that can adapt to the unexpected. They will remember that they were part of something larger than themselves, a mission that transcended individual careers and lifetimes, a journey that began in the 1970s and continues still, pushing outward into the cosmos, carrying a piece of humanity farther than it has ever gone before. The Voyager missions demonstrate what humans can accomplish when we commit ourselves to long-term goals, when we build institutions and teams capable of sustaining effort across decades, when we value knowledge and exploration for their own sake. They show that we can create things that outlast us, that we can solve problems that seem insurmountable, that we can reach beyond our immediate circumstances to touch the infinite. These are lessons worth remembering as we face the challenges of the present and the uncertainties of the future. The spacecraft themselves will eventually fail, their systems succumbing to the inevitable decay of time and the harsh environment of space. But what they represented, the human spirit of exploration and discovery that motivated their creation and sustained their missions, that remains. It is embodied in the people who built and operated them, in the scientists who analyzed their data, in everyone who looked at Voyager images and felt wonder, in anyone who thinks about those distant machines drifting through the darkness and feels connected to something larger than themselves. The Voyagers are more than spacecraft. They are symbols of human potential, reminders of what we can achieve when we dare greatly, when we look beyond our limitations and reach for the stars. The question of what the Voyagers mean extends far beyond their scientific achievements and technical accomplishments. These spacecraft have become cultural touchstones, symbols that resonate in ways their creators might not have anticipated. They appear in literature, art, music, and film. They inspire philosophical reflection about humanity's place in the cosmos. They serve as mirrors in which we see ourselves reflected, our ambitions and limitations, our hopes and fears, our capacity for both wonder and self-destruction. Understanding the Voyager's significance requires looking beyond the data they transmit and considering what they reveal about the species that built them. The iconic photograph known as the pale blue dot stands as perhaps the most profound image associated with the Voyager missions. On February 14, 1990, at Carl Sagan's urging, Voyager 1 turned its camera back toward the inner solar system from a distance of 6 billion kilometers. Earth appeared as a tiny point of light, less than a single pixel in the vast darkness, suspended in a beam of scattered sunlight. The image is technically unremarkable, grainy and dim by modern standards, but its meaning transcends its resolution. It shows our world as it actually is in cosmic context, infinitesimally small, utterly fragile, alone in an incomprehensible vastness. Sagan's reflection on that image has become one of the most quoted passages in science writing. He wrote about everyone we have ever known living on that pale blue dot, about every human drama and achievement playing out on a mote of dust suspended in a sunbeam. He wrote about the absurdity of our pretensions, our imagined self-importance, the delusion that we have some privileged position in the universe. He wrote about the responsibility this perspective places on us to be kind to one another, to preserve and cherish that pale blue dot, the only home we have ever known. The photograph and Sagan's words combine to create a moment of collective consciousness, a shared recognition of our cosmic context that cuts across cultures and ideologies. The pale blue dot image works as a psychological mirror. It forces a shift in perspective that many describe as transformative. Astronauts who have seen Earth from space often report a similar experience, sometimes called the overview effect, a cognitive shift in awareness that comes from seeing the planet as a whole, without borders, floating in the void. The pale blue dot provides a version of that experience to anyone willing to contemplate it, a reminder that our divisions and conflicts, our nations and ideologies, are human constructs imposed on a world that is ultimately one unified biosphere, one interconnected system of life, clinging to the surface of a small planet in an ordinary solar system in an average galaxy among billions. This perspective has ethical implications. If we truly understand our cosmic insignificance, our isolation, the fact that we are alone on this fragile world with no one coming to rescue us from our own mistakes, how can we justify continuing to destroy our environment, to wage wars over arbitrary boundaries, to let preventable suffering continue? The pale blue dot serves as an argument for global cooperation, environmental stewardship, and a reordering of priorities away from parochial concerns toward existential ones. Whether people actually change their behavior based on this perspective remains an open question, but the image at least provides a framework for thinking about what matters. The Voyagers also raise questions about the value of exploration itself. Why do we explore? What drives this impulse to venture into the unknown, to climb mountains and cross oceans and send machines to distant planets? Some argue that exploration is a biological imperative written into our genes by millions of years of evolution. Our ancestors, who were more curious, who ventured beyond familiar territory, who explored new environments, were more likely to find resources, avoid local disasters, and ultimately survive and reproduce. We are their descendants, inheritors of their curiosity and restlessness. Others see exploration as a cultural phenomenon, a choice rather than an imperative. Different societies at different times have valued exploration to different degrees. The Chinese treasure voyages of the 15th century reached Africa and could have continued to Europe and beyond, but China chose to turn inward, to stop exploring, to focus on internal matters. European exploration of the Americas was driven by specific historical circumstances. Competition between nations, the search for trade routes, religious motivations, technological capabilities. It was not inevitable, but contingent on particular conditions. If exploration is a choice, we must ask whether it is the right choice, whether the resources devoted to exploring space could be better used addressing problems on Earth. The Voyager missions embody this tension. They cost billions of dollars, required the efforts of thousands of people, consumed resources that could have been allocated elsewhere. Did they provide sufficient return on that investment? The scientific data alone probably justifies the cost, but scientific data is not the only consideration. The missions inspired people, advanced technology, demonstrated international cooperation, provided perspective on our place in the cosmos. These intangible benefits are difficult to quantify, but arguably as important as the scientific findings. Yet there remains legitimate debate about priorities, about whether space exploration represents the best use of limited resources when poverty, disease, and environmental degradation afflict billions of people on Earth. The Voyagers also illuminate the relationship between short-term thinking and long-term projects. The spacecraft were designed and built by people who would not live to see their journey into interstellar space. The engineers who solved the technical challenges, the scientists who planned the observations, the administrators who fought for funding, they all worked toward a future they would not experience. This kind of multi-generational thinking seems increasingly rare in modern society, where quarterly earnings reports and election cycles drive decisions, where immediate gratification often trumps long-term planning. The Voyagers remind us that some achievements require patience, sustained effort across decades, commitment to goals that transcend individual lifetimes. There is something almost sacred about this long-term perspective. It acknowledges that we are part of a larger continuum, that we inherit from those who came before and have responsibilities to those who come after. The Voyagers were gifts to the future, both to our own descendants who will analyze their data, and to hypothetical alien civilizations who might find them millions of years hence. They represent a kind of faith in the future, a belief that the journey matters even if we never see its end, that the knowledge gained and the act of exploration itself have intrinsic value beyond any practical application. The missions also demonstrate the power of human cooperation. The Voyagers required collaboration among scientists from different disciplines, engineers from different specialties, institutions in different countries. The Deep Space Network includes facilities on 3 continents, operated by different teams but coordinated seamlessly to maintain constant communication with the spacecraft. The planetary flybys required international cooperation on observation campaigns, with astronomers around the world using ground-based telescopes to complement Voyager's observations. The data has been shared freely with the global scientific community, analyzed by researchers in dozens of countries, incorporated into teaching and research worldwide. This cooperation stands in stark contrast to the geopolitical conflicts and competition that often dominate human affairs. The Voyager missions were conceived and executed during the Cold War, when the United States and Soviet Union maintained vast nuclear arsenals aimed at each other, when proxy wars raged across the globe, when ideological divisions seemed unbridgeable. Yet the missions themselves were peaceful, scientific, aimed at understanding rather than domination. The Golden Records explicitly spoke of hope for a unified human civilization, for solving our problems and joining a cosmic community. They represented the better angels of our nature, the part of us that seeks knowledge and connection rather than conflict and conquest. Whether this represents a realistic vision or naive optimism remains debatable. Human history is filled with conflict, competition, and violence. Cooperation often breaks down under pressure. The international cooperation that characterized the Voyager missions has not prevented wars, has not solved global problems, has not created the unified civilization that Sagan and others hoped for. The same nations that collaborated on space exploration have continued to compete, sometimes violently, in other arenas. The same species that sent golden records into space declaring peace and goodwill has also created weapons capable of destroying all life on Earth. Yet the fact that we are capable of cooperation, that we have achieved remarkable things when we work together, suggests that alternatives to conflict are possible. The Voyagers prove that humans from different backgrounds, with different perspectives and skills, can unite around shared goals and accomplish extraordinary feats. If we can do this for space exploration, why not for addressing climate change, poverty, disease, or other global challenges? The missions provide a template, an example of what becomes possible when we transcend our differences and focus on common objectives. The Voyagers also raise profound questions about time and mortality. The spacecraft will outlive everyone who built them, everyone who operated them, everyone alive today. They will continue their journey for tens of thousands of years, eventually passing near other stars, drifting through the galaxy for timescales that dwarf human history. Long after our civilization has transformed or disappeared, long after all records of our existence on Earth have eroded away, the Voyagers will remain, silent witnesses to a vanished species that once looked up at the stars and wondered. This perspective forces us to confront our own mortality, both individual and collective. We are temporary, ephemeral beings living in a universe that operates on timescales we can barely comprehend. Stars are born, evolve, and die over billions of years. Galaxies collide and merge over eons. The universe itself may continue expanding forever, eventually reaching a state of maximum entropy where no organized structures remain, no energy flows, nothing happens at all. Against this cosmic backdrop, human existence is briefer than an eye blink, our entire history a fleeting moment in the vastness of time. Yet we matter. We are the universe becoming conscious of itself, matter organized in such a way that it can observe, understand, and contemplate its own nature. We are the means by which the cosmos explores itself, learns about itself, creates meaning from meaninglessness. The Voyagers are extensions of this consciousness, technological organs of perception reaching farther than our biological senses can extend, sending back information about regions we cannot directly experience. Through them, we have touched the surface of worlds no human will likely ever visit in person. Through them, we have sampled the interstellar medium, measured the boundary of our sun's domain, ventured into the space between stars. The scientific legacy of the Voyagers is beyond dispute. They revolutionized planetary science, transformed our understanding of the outer solar system, revealed worlds of stunning complexity and beauty. The discovery of active volcanism on Io, the hints of subsurface oceans on Europa and Enceladus, the complex dynamics of planetary rings, the bizarre magnetic fields of Uranus and Neptune, the active geology of Triton, these findings fundamentally changed how we think about moons and planets. They showed that the solar system is not a collection of dead or dying worlds, but a collection of dynamic, evolving systems, each with its own unique characteristics and history. The interstellar measurements are equally significant. The direct sampling of the local interstellar medium, the mapping of the heliosphere's boundary, the measurement of cosmic ray spectra and magnetic fields, all provide data that cannot be obtained any other way. Future missions to the outer solar system and beyond will build on Voyager's findings, using them as baseline measurements against which new observations can be compared. The data will remain valuable for decades, perhaps centuries, as our understanding of astrophysical processes continues to develop. But perhaps the most enduring legacy is inspirational rather than scientific. The Voyagers have inspired generations of scientists, engineers, and ordinary people to look up, to wonder, to imagine what might be possible. They have shown that humans can accomplish extraordinary things when we commit ourselves to ambitious goals. They have provided perspective on our place in the cosmos, reminding us of both our insignificance and our potential. They have demonstrated that exploration is not just about acquiring knowledge, but about expanding consciousness, about pushing the boundaries of the known, about daring to venture into the unknown, despite risks and uncertainties. Every person who has looked at a Voyager image and felt wonder, every student who decided to pursue science or engineering because of the missions, every scientist whose research built on Voyager data, every person who contemplated the pale blue dot and thought differently about Earth and humanity, all are part of the mission's legacy. The impact extends far beyond the immediate scientific findings to touch millions of lives in ways both measurable and immeasurable. This kind of cultural influence is difficult to quantify, but arguably as important as any technical achievement. As the end of communications approaches, there's a sense of impending loss, but also gratitude and celebration. The Voyagers have far exceeded their designed mission parameters, both in duration and in scientific return. They have functioned reliably for nearly 5 decades, endured conditions their designers only hoped they could survive, adapted to problems and challenges through human ingenuity and engineering creativity. They have given us more than we had any right to expect, more than anyone dared hope for when they launched in 1977. The fact that they are still operating at all is miraculous, a testament to the quality of their design and the dedication of the people who have maintained them. When the final signal arrives, when the last data is received and the spacecraft falls silent, it will mark the end of one of the most successful and longest-running missions in the history of space exploration. There will be sadness, certainly, the sense that we are losing something precious, that a connection maintained across billions of kilometers for half a century is being severed. But there should also be pride and satisfaction. We did this. Humanity, for all its flaws and limitations, built these machines and sent them to the stars. We accomplished something extraordinary, something that will echo through history, something that demonstrates the best of what we can be. The Voyagers will continue their journey long after they fall silent. In 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. The spacecraft will be cold and dark by then, its power exhausted, its instruments dead, but it will still carry its golden record, still bear evidence of its origin and purpose. If some intelligent being encounters it, if they manage to decipher the record's contents, what will they learn about us? What will they think of this species that sent messages into space declaring peace and goodwill while simultaneously perfecting weapons of mass destruction? What will they make of our art, our music, our greetings in dozens of languages? Will they understand? Will they care? Will they even exist? These questions are ultimately unanswerable, but they are worth asking because they force us to think about who we are and who we want to be. The golden records represent our ideal self-image, how we wanted to present ourselves to the cosmos. The reality, of course, is more complex and often darker. We are a species capable of both extraordinary beauty and terrible violence, capable of creating art and music and spacecraft, but also capable of war, oppression, and environmental destruction. The Voyagers carry only one side of this duality, the hopeful side, the aspirational side. They are messages from our better selves to whatever futures await. Perhaps that is their ultimate value. Not as scientific instruments, though they have been superb at that task. Not as technological achievements, though they represent remarkable engineering. But as symbols of human potential, reminders of what we can accomplish when we commit ourselves to something larger than our immediate interests. when we work together toward common goals, when we dare to reach beyond our limitations and explore the unknown. They show us at our best, and in doing so, they challenge us to live up to that image, to become the species we claim to be in those messages we sent to the stars. The cosmic mystery that the Voyagers have helped illuminate is not just about the nature of space, the properties of planets, or the characteristics of the interstellar medium. It is about ourselves, about what it means to be conscious beings in an unconscious universe, about how we create meaning in a cosmos that seems inherently meaningless, about why we explore and what we hope to find. The Voyagers are questions as much as answers, prompts for reflection on the deepest issues of existence and purpose. In the end, the journey matters more than the destination. The Voyagers have no final destination, no endpoint to their voyage. They will drift through space essentially forever, their paths determined by gravity and momentum, their fate unknown. But the journey itself, the act of sending them forth, the decades of discoveries and insights, the inspiration they provided to millions of people, the perspective they offered on our place in the cosmos, these are the true achievements. These are what endure, not in the spacecraft themselves, but in the minds and hearts of those touched by their story. The great journey beyond the solar system continues. Every day, the Voyagers move farther from the sun, deeper into interstellar space, into regions where no human-made object has ever been. Every day, they send back data about their environment, measurements that help us understand the galaxy we inhabit. Every day, they carry their golden records farther into the unknown, messages from humanity to the cosmos. And every day, they remind us that we are explorers, that we are curious, that we are capable of accomplishing extraordinary things when we dare to try. When the spacecraft finally falls silent, when the last transmission is received, and the deep space network antennas point elsewhere, something will be lost. We will no longer have that direct connection to our distant explorers, that daily confirmation that they are still out there, still functioning, still sending back information from the edge of known space. But something will remain. The data they gathered will continue to be analyzed for generations. The images they captured will continue to inspire wonder. The example they set will continue to challenge us to reach farther, to dream bigger, to never stop exploring. And somewhere in the vast darkness between stars, two small machines will continue their eternal journey, carrying with them the hopes and dreams of a species that looked up at the night sky and refused to accept that those distant lights were forever beyond reach. They are proof that we were here, that we wondered, that we tried. They are monuments to human curiosity and courage, to our endless fascination with the unknown, to our unquenchable desire to understand the universe and our place within it. They are Voyagers, travelers on a journey that will never end, bearing witness to the cosmos on behalf of all who built them, all who operated them, all who were inspired by them, all who dared to imagine what might lie beyond the next horizon. The mystery of the cosmos remains, vast and deep and ultimately unknowable. But the Voyagers have given us glimpses, hints of understanding, pieces of the puzzle. They have shown us worlds we never imagined, revealed complexities we never suspected, measured boundaries we never knew existed. They have expanded the sphere of human knowledge and pushed back the frontiers of the unknown. And in doing so, they have fulfilled their ultimate purpose, not to answer all questions, but to inspire new ones, to ensure that the great journey of exploration and discovery continues, that each generation reaches a little farther than the last, that humanity never stops looking up at the stars and asking what lies beyond. This is the legacy of the Voyagers, not just the data, not just the images, not just the scientific discoveries, but the inspiration to continue exploring, to keep asking questions, to never be satisfied with what we know when so much remains to be discovered. As long as humans look to the stars and wonder, as long as we build machines to extend our reach and our senses, as long as we dare to venture into the unknown despite all the risks and uncertainties, the spirit of Voyager lives on. The journey continues, and it will continue as long as there are humans to carry it forward, as long as there is curiosity and courage and hope. The Voyagers may someday fall silent, but their message echoes still, calling us outward, upward, onward, into the infinite mystery of the cosmos that surrounds us. The cosmos we are only beginning to understand, the cosmos that is our home, our heritage, and our destiny.